Hello, everyone. So I hope you are all enjoying the conference so far. I am Bimlesh Wadhwa from National University of Singapore. I'm here today to introduce the next keynote speaker, Miles Berry. Miles is a key figure in UK's Computing at School program. He is a principal lecturer in computing education at the University of Roehampton. Over the years, he has contributed to a number of computing education related projects, including the National Curriculum Computing Programs of Study, Switched On Computing, Barefoot Computing, Quick Start Computing, CAS TV, Project Quantum, Hello World, and many others. He's a chartered fellow of the British Computer Society and also serves on the BCS Academy of Computing Board and on the Management Board of Computing at School. He also serves on the academic board of England's National Centre of Computing Education. Miles was the international representative on the CSTE's board of directors and continues to be a member of its professional development committee. He is also an active member of the Raspberry Foundation. Glad to have you here, Miles, for this keynote. A very warm welcome from all of us here at Singapore. And now I hand it over to you for your keynote, 2 types of computational thinking.
Thank you so much. It is such a pleasure to be able to be online with you all. And thank you so much for the invitation to come and offer at least some thoughts on this idea of computational thinking with you. Bear with me a moment whilst I set up my screen sharing thing at this end. There we go. Hopefully that's working all right. So you might be a little bit scared by the title here, but we as computer scientists or computing educators recognize immediately that the 1-0 there is of course not denary but binary, because I am going to just talk about 2 types of computational thinking over the next 45 minutes or so. I want to start by clarifying, or a lot of this talk is about clarifying what we actually mean by computational thinking, or CT, as I'm abbreviating it here. As Bimlesh explained, I was part of the panel that drafted England's computing programs of study, a good sort of, what was this, 2013, that these were published. And we start with this really ambitious opening sentence: a high-quality computing education equips pupils to use computational thinking and creativity to understand and change the world. I see these as pairwise things, that the computational thinking there is about understanding the world and the creativity is about making a positive change to that world. Our national curriculum doesn't really define computational thinking. It doesn't define many of the terms that it uses. So we need to think a little about that. I think that computational thinking is not thinking like a computer, despite all of the activities that you will see in schools of children putting themselves in place of the turtle or in place of a robot and doing entirely automated actions. I think that is close to programming children rather than teaching children how to program. It's not, computers don't at the moment think. When they do think, it's unlikely to be something that we'd want to necessarily replicate ourselves. Perhaps more controversially, I don't think when we're thinking about this as a school subject, it is even thinking like a computer scientist, because they're like 9-year-olds or 16-year-olds. They're not computer scientists. They might borrow or learn some of the ways in which computer scientists approach problems. And interestingly, for Donald Knuth, the idea of this sort of thinking like a computer scientist pretty much defines the discipline of computer science. He says right at the start of it, computer scientists were those who gathered together in university departments because they had this particular peculiar way of thinking about things. So let's start by thinking computational thinking. Yeah, that is a peculiar way of thinking about things. As I say, I don't think it's reasonable to expect children in school to think like computer scientists, just as we can't expect them to think like scientists, because they're not computer scientists, because they're not scientists. The way a novice approaches a problem is different from an expert. An expert has all of that domain knowledge to draw on in a very flexible, powerful sort of way. They're making connections between different areas of the discipline. We can help them on the journey to becoming computer scientists or using these approaches to solving problems in their later life and their later study, but don't expect too much of them at that early age. What our national curriculum in England does do is give some sense of what progression looks like in this area of the curriculum away from the programming bit. So for our under fives, which isn't even on the national curriculum, we talk about solving problems, making predictions, testing ideas, planning, checking, changing strategy, reviewing. Pretty much the whole of it is established in kindergarten, in nursery. And then that sort of sense of progression, of logical reasoning, of logic being a big part of what we think computational thinking looks like, at least when it's put down into the detail of things that children should be taught, and sort of progression as we get to decomposition and abstraction, and then what ends up on the exam specifications. So yes, I think we have two ways of thinking about computational thinking, and I want to deal with each of these in turn. I'd be really interested in your views, although we don't have that sort of interactivity here to do the show of hands thing if we were together in a conference room at the moment, about is it type 0 applying the approaches of computer science to problems in other disciplines? Or is it more type 1 here, this idea of finding an automatable, a programmable solution to a problem? Or do you reject my binary choice there as a false dichotomy, which may well be the right answer? So let's start with computational thinking type 0, as I'm calling it for today. This idea of applying computer science approaches elsewhere. And this really is what Jeanette Wing had in mind when she started writing about computational thinking back in 2006. She talked about it as a fundamental skill for everyone, that it deserves a place in school curricula alongside reading, writing, and arithmetic, that computational thinking was as important as basic literacy and basic numeracy. That's a very, very strong claim to make. She says it involves solving problems, designing systems, understanding human behavior by drawing on the concepts fundamental to computer science, which immediately begs the question, what are these concepts fundamental to computer science? Would you count binary as a concept fundamental to computer science? Wing certainly includes computability on that list. There are some things which are solvable, some things which are not. She includes abstraction on that list, this idea of managing the complexity of complex systems. Cynthia Selby, John Woolard put together in 2014 the literature review, looking at all of the definitions that people are given, not so much the definitions as that sort of categorization of the parts of computational thinking, and come up with criteria for, yes, we should include this. It is a thought process. It does involve abstraction. We don't see it as merely problem solving, because that's a much more general approach, and not all problem solving is necessarily computational thinking. Their work was deeply influential in what we did for barefoot computing, as indeed was Julia Briggs's work for Somerset County Council, in identifying this cluster of concepts on which the computational thinker might draw, this idea of they're deterministic machines. We can predict what they will do when given certain input and given certain programs, that computational thinking involves coming out with an algorithm, a sequence of steps or a set of rules in order to solve something. It involves abstraction. One of the things that I was so pleased about with Barefoot is that we also looked at the right-hand side of this, that computational thinking isn't merely about a set of concepts to learn, but a set of approaches to apply. And I think this is really powerful when it comes to experiencing computational thinking in the school setting, about experimenting and playing, or tinkering, as we call it, about learning through making, with a nod in the direction of Seymour Papert. They're fixing things when they go wrong. They go wrong a lot in our subject, of keeping going when things get difficult, of collaborating. Now, none of this is unique to computer science, but what we're doing here is saying these are some of the concepts, some of the ways of working that seem fundamental to how computer science or how software engineering gets done in the real world. Let's bring those into the school curriculum and give all pupils some experience of these, because these are so important in this modern age. The Barefoot work was influential in Linda Lucas's much more visually appealing taxonomy of computational thinking. And it's lovely to see the things that Linda has added on to this, this notion of data, which is certainly something which we should have included there. And I think, yes, the creativity is absolutely important. We acknowledge that in the Barefoot list. Given that that's our approach to computational thinking, type 0 computational thinking, applying the ideas of CS to other subjects that they're studying in school, I think Grover and P ask a very, very sensible question about what would you actually expect that to look like in practice, if children are participating in a curriculum that is designed to develop computational thinking, what does that look like? How could it actually be measured? I think this sort of bit by bit, the fundamental concepts and approaches applied more generally approach, we see this idea of computational thinking across the curriculum. And Dijkstra's misattributed, or the quote that is misattributed to Dijkstra, about you don't actually need computers in order to do computer science. Computer science is no more about computers than astronomy is about telescopes, gives teachers, gives school systems the opportunity to step away from the screen. They wouldn't it have been lovely to have been able to do a little bit more stepping away from the screen over the last 15 months or so. So being able to do these unplugged activities, being able to learn these fundamental concepts and approaches without necessarily having to do any programming, without necessarily having to use a computer. Really influential paper by Barr and Stevenson back in 2011 looked at how some of these concepts, capabilities of computational thinking could be developed elsewhere in the curriculum. So you can teach algorithms, for example, by doing long division, by working out factoring, by using carries in addition and subtraction. This is an algorithm. It's a sequence of steps in order to solve a particular type, particular class of problems. You could, for example, use, taking another example, species classification as problem decomposition here. So all of the ideas of computational thinking, Barr and Stevenson maintain, can be taught within the context of other subjects. And certainly before the age of 5, in that nursery and that kindergarten curriculum, so much of the foundations of computational thinking can be laid far, far away from any sort of screen or machine. So we expect, this is again the English curriculum, expect that children should realize that their actions have an effect on the world. This is starting, laying the foundations of logical reasoning. Plan and think ahead how they will explore or play with objects. This idea of planning, fundamental to the idea of, yes, software engineering, but also the notion of the algorithm. Take part in simple pretend play. Isn't that at least part of what we mean by abstraction, of representing something complex in the real world with something much simpler in a smaller space? What does this look like in practice? We have a couple of chaps here trying to solve some difficult problems, planning ahead, thinking about what's going to happen, the effect of their actions. We have children sorting and classifying objects according to rules. We have a whole team of people working together to solve a problem. I'm interestingly, by the gender divide here. You notice the boys are getting on with the work whilst the girls take on a managerial or supervisory role in this picture. And we also have, teachers, practitioners putting on their desk the thinker saw, the trier saw, the explorer saw. Isn't that the sort of attitudes to work that you'd want in your computing or computer science lessons too? So much of this foundational work of introducing them to concepts and approaches fundamental to computer science does seem to take place within the context of food. So for barefoot computing, we have lovely activities such as sharing sweets. We have an algorithm for how would you share sweets between 2 people, 1 for me, 1 for you, until there are no sweets left. Sharing between 3 is a similar pattern. So we have not only a sequence of steps here, but the beginnings of patterns and generalization. Of course, this is different from how a computer does division, where repeated subtraction is our approach rather than an equal sharing. We have lovely activities which involve, what's your recipe for pizza? I've done this with rooms of teachers and rooms of students, and everybody goes at a certain level of abstraction with this. And, there are those who are destined for their career in senior leadership teams who say, phone Domino's or phone the local pizza restaurant is their approach to making pizzas. And there are others who go at a much, much more granular level of detail about kneading the dough, about mixing the dough together. I've never yet worked with somebody who's started with first raise your herd of buffalo or first plant your herd of wheat. Everybody uses pre-built components when they make pizza. And of course, we have the general approach to making all pizzas, and then you add the toppings in to give the particular type you want. So introducing the idea of variables there and patterns again. And it turns out that now somebody has actually automated this solution. There are machines in Rome now which will very happily sort of just, the robot will make you a pizza. I can make no claim for the quality of this pizza. You will see very familiar jam sandwich algorithms of what are your sequence of steps to make a jam sandwich or jam and peanut, jelly and peanut butter sandwich. In England, of course, we have, as part of our statutory requirements in school, to promote fundamental British values. And what could be more fundamental as a British value than a nice cup of tea? And so you will have children learning the algorithm or writing the algorithm for making a cup of tea, which is a very, very important skill for them to learn. Interestingly, the British Standards Institute has a specific standard for what tea should be like, which actually answers the fundamental question here about whether you had the milk before or after the tea is poured into the pot. Prepare the liquor as described in 7.2.1, use of a sub-procedure there, pour it into the bowl after the milk, and even gives a reason for that. So you have all of these lovely unplugged activities, which I think do give children some idea of what we mean by an algorithm, or what we mean by decomposition, or what we mean by pattern. Are they drawing on the fundamental concepts of computer science? I'm not sure that they are, but they are learning about these fundamental concepts of computer science, and perhaps will be able to apply them to slightly more meaningful problems subsequently. There is room for some skepticism about these unplugged approaches, and there is at least one study there which says that actually yes, it teaches the concepts. Children go out of these unplugged lessons knowing about these things, but they don't seem to enjoy them as much as lessons where they are actually using a computer, where they are making something on screen. Their desire to study CS seemed somewhat reduced by a focus on just unplugged approaches. So I think there may be a case for plugging this back in. And I think Mark Gusdale, in his Learner-Centered Design in Computing Education 2016 book, makes a really important point, arguing that there's not been a study since Wing's 2006 paper that's actually demonstrated that students in a computing class transferred that knowledge from the class into their daily lives. Learning about algorithms, learning about pattern recognition, learning about decomposition doesn't necessarily make you any better at making pizza or baking bread or tiling a bathroom floor. Perhaps it helps you understand these concepts of computer science, but the transfer effect is really very limited, according to the research which Gusdale is citing. So what does this look like in terms of a Venn diagram here? It seems that we have this larger domain of computational thinking, according to this approach, within which of problem solving, within which we might cite this subdomain of computational thinking. And then over to one side, there seems an entirely separate body of knowledge, which is around coding. And so often you will see, or I see this taught in schools of, we're learning about computational thinking, let's make our pizza. Now we're learning about scratch programming, follow these instructions. Again, the sort of programming a child rather than teaching a child to program type approach. Sometimes you get some bit of overlap. Okay, you've learned how to do this as an unplugged activity. Now let's see what this looks like coding. I'm not convinced that this is the best way to do it, and I don't think Mark is particularly convinced by this idea either. I'd like to promote a more critical view of CT, top right of the tweet there. Are we moving to a world where the poor get CT without programming? Much cheaper to resource this sort of computational thinking, and the rich get real computer science that advances their economic opportunity, and wonders if computational thinking even exists. I think it does. I think it lies at and I think Jeanette Wing has moved her thinking on now to reflect a deeper, a better understanding of this, which is my type 1 computational thinking, this idea of finding the automatable solution to a problem. Tedder and Denning's 2016 paper, so influential in this. Computational thinking, powerful mental tools for people who design computations. This is the purpose of it. Computational thinking, yes, the fundamental concepts and approaches of computer science, but the purpose of those is for designing computation. If you'll allow me, computational thinking without computation is really just thinking. There's no need to make exaggerated claims, notably the transfer of CT skills across domains, or because CT is better than other ways of thinking. being able to design a computation, being able to get a computer to help you solve a problem is a skill worth teaching in and of itself. Yes, okay, not in and of itself. It has extrinsic value. It helps you solve problems for other people. It helps you solve problems in your own studies. It helps you solve real problems out there in the real world. Being able to get computation done, being able to get the machines to help you is a really important thing. Yes, being able to make pizza is important too. Okay. So Wing's more recent definition of computational thinking in 2014, the thought processes involved in formulating a problem and expressing its solution in such a way that a computer can effectively carry out mental activity in formulating a problem to admit a computational solution. So I think this moves our thinking much, much further on than just drawing on the approaches of computer science. This gives us something which we can assess, which we can teach too. Can you, given a problem, come up with a solution that could be programmed into a machine? It isn't the programming. It's the thinking that comes before the programming. For the Quick Start guides, which were funded by the Department for Education here as initial professional development for teachers in English schools, I attempted my own definition of this, very, very much influenced by that work from Wing there. In order to get a computer to help you solve a problem, you go through two steps. Think about the steps needed to solve the problem, and then use your technical skills to get the computer working on the problem. This applies to making a presentation just as much as it applies to creating a bubble sort program in Scratch or wherever. And I think it's the thinking that's undertaken before starting work on the coding that's the computational thinking, before starting work on the computer, looking at a problem in a way that a computer can help us solve it. Okay, so this is my type 1 computational thinking, and I think it's far, far more powerful than just drawing on these approaches. You're welcome to disagree. I look forward to our discussion later. Brennan and Resnick, I think, go even further. They identify computational thinking as housing these concepts, practices, and perspectives. The perspectives is very much like our tinkering and debugging. In fact, let's have a look at what they put on to that. So the concepts, they say, are part of computational thinking are things like sequences and loops and events, very much Scratch-based, isn't it? Parallelism, again, Scratch does that very, very well. Python, not so much. Conditionals, operators, and working with data. And all of this seems very, very close to programming concepts rather than more sort of abstract, general computational thinking concepts. So their thinking seems to be this is very much about you programming a computer to help you solve a problem. And look at the practices that they identify: incremental and iterative, testing and debugging, reusing and remixing, abstracting and modularizing. All of this takes us very, very close to the layer of code there, automatable solution. And I think they would suggest the automation of those solutions. So with an acknowledgement to Wirth's much more meaningful definition of programming as algorithms plus data structures, I would offer, particularly in the school context, this idea of programming is made up of these two bits: the algorithms and then the implementation of those algorithms as code in a particular language. I think Schneiderman and Mayer back in 1979 captured it much more verbally there, about you've got the semantics and the syntax. Programming is difficult because you're doing two things at the same time. You're thinking about how to solve the problem and then expressing that in a particular formal language that the machine can follow for you. And that does bring its own challenges. So the computational thinking is about the semantics, about how I'm going to go about solving this problem. And this is a thing worth teaching, because just attempting to rush straight into the syntax is going to be hugely problematic. So perhaps my diagram ought to look a little bit more like this. Yes, we have this big domain of problem solving out there, within which sits some computational thinking, and then within that we have the expression of these solutions as a sequence of instructions that the machine itself can follow, the actual coding bit of this, which I think is really very, very powerful. So how do you go about teaching this? Find interesting problems which are capable of automated solutions. One of the richest territories to explore for this is the idea of programming games. And this has a long and noble history within our domain. Game programming, predates Colossus, predates the cracking of the Enigma and Lorentz ciphers there, as I'll show you in a moment or two. So we have, one of the games which I would teach to students, which I've taught to pupils in school, is this idea of the game of NIM. And games are different from play because games have rules and games have objectives, much in some sense like school. School is a game, but school is definitely not just play, is it? So in NIM, we start with 3 piles, a 7, a 5, and a 3. The players take it in turns, playing with the same pieces on the same board, which is a property of these NIM-like games. In each move, you can take one or more match from only one pile. Your objective is to be the player who takes the very last match from this, and the pieces you use, as it says, piles of matches. So, if we had more time together, if we were together in a lovely conference room with tables and suites or whatever, then we could spend some time playing the game of NIM. Now, I'm going to leave that as an exercise for you after this talk. Turns out that there is a very, very simple recipe for winning at NIM, which is to make winning moves. And that kind of goes hand in hand with avoiding the losing moves. What does a winning move look like? Well, it's one which makes your opponent make a losing move on their very next turn. How do you avoid a losing move? Well, you don't let your opponent make a winning move. Simple as that. We could play NIM. NIM is an automatable game. So with a little bit of luck, I can move in Digimath's implementation of NIM in Scratch. And we should be able to click on the thing and play the game. Press 1 to go first or 2 to let the computer start. I think letting the computer start seems a high-risk strategy. So I'm going to go first here. 1, 2, or 3. Let's take, shall I take 1 from the top? Number of stones, 1 from the top. It's thinking, takes a little while. Ooh, now look what it's done. It's taken another 1 from the top. I'm going to go for the bottom row and take all 3 of those. It takes 1 from there. I'm going up to the top row, taking 1 of those. And, oh, I've got my turn now. 1 from there. Sorry, this must be fascinating watching this working out. I'm going to go for the second row, take 1 from there. And I hope some of you are seeing how this is going to go now. I'm going to take 1 from there. Okay, and I think that leaves the last one to be me. Okay, and I win. Okay, so the interesting thing here, of course, is what are the winning moves? What do they all have in common? And if you watch children learning to play this game, you'll see that their strategy evolves. And sooner or later that they will assemble a list of, okay, if I leave the board in this position, I'm in a winning position. So 1-1, definitely a winning position. We can reason about that logically. And all of the other ones on the list there are winning moves. So at each point, as long as you move into one of those winning positions, you can guarantee that the rest will work. Now, there's a deep property to this. Some of you may have realized already that the bitwise XOR, exclusive OR, of these sets of numbers here is 0 in all of these cases. And in fact, winning moves are those which have this bitwise XOR as 0. Non-winning moves have a bitwise XOR of 1. So there is a distinguishing characteristic there. Whether you'd expect primary or indeed lower secondary pupils to spot that is a whole other matter. You've got that going on. How is this helping them with computational thinking? Well, all of those fundamental concepts and approaches that we've talked about in computational thinking 0 are evident in playing this game and in programming a solution to this game. Key stage 3 of our English National Curriculum for Computing: design, use and evaluate computational abstractions that model the state and behavior of real-world problems and physical systems. How are you going to represent this board as a data structure? What are the rules of this game? What do they look like in practice? What is your optimal strategy at each point for winning this game? What if you're in a position which is not winning, as the computer found itself? What do you do then? Just run in circles, screaming and shouting, but it's not fair? Or do you just make a random move and hope that your opponent makes a mistake? So there's so much rich territory to explore in playing and then perhaps programming a game like this. This particular game has, as I say, a long and noble history. You have here an illustration from the 1939 World's Fair in New York, before the beginning of the Second World War, of a machine that was programmed to play NIM. The patent for this is available online, and it's all done with electromechanical relays. So before Turing built Colossus, or as a computer to crack the Lorenz cipher, before Johnny von Neumann was building the ENIAC, they had built a computer to play this silly game of NIM. And again, 1951, the Festival of Britain in London, similar sort of machine. And there are stories of queues of people around the block waiting to play this. And of course, bringing that up to date, you have all of the work that's going on at DeepMind, funded by Alphabet, funded through Google, to create programs that much of the work they started with in artificial intelligence was about building computer programs that could play games better than any person had been able to do that. Other territory that we could explore here. So again, in barefoot computing, we have this idea of learning the rules of phonics as an illustration that not all algorithms are about sequences of steps to follow, that sometimes we express our algorithms as a set of rules that we apply. So if you see if you hear the phoneme or, how do you write that down as a grapheme? How do you write that down as characters on paper? Well, it depends on the context. There are rules that we follow here. And of course, with written English, there are always exceptions to these rules. So we have, understanding the idea of an algorithm this way, but it becomes much, much more interesting when we attempt to automate that algorithm. And so text-to-speech, teaching a machine to read text to you. And okay, that's hidden inside the little speak block here in the Scratch extensions, but creating a spelling test in Scratch, that's a really interesting programming challenge, because you cannot simply display the question on screen. You have also, of course, the reverse operation. So many of our primary pupils will be very, very familiar with the asking questions of Siri or the Google Assistant or Alexa in order to get homework done. How does that even work? And we can start teaching this. We can teach them about how a machine would recognize their voices, but they can also use that in their code using, this is Dale Lane's extensions to Scratch, machine learning for kids, which bring in the speech recognition there. So getting Scratch to do a reading test for pupils. I love this idea of taking these big ideas of artificial intelligence and having children start to make use of them in their own code as a way to understanding this. And very often we're going to be using search as an example of algorithms that children should know. This is fundamental to so much computer science. What is your optimum algorithm for searching through a list of things? Children are learning this, yes, in an unplugged way at first. Finding a word in a dictionary, is it halfway through? Is it a quarter of the way through? Is it 3/8 of the way through? Actually, dictionary search is really radix search, because you look at the initial letter, which is even more efficient. They will play this over in their maths lessons. I'm thinking of a number, ask me some questions. The interesting thing for me is that when you see this game being played in a maths lesson, children are encouraged to come up with really interesting mathematical properties of the number. Is it a prime number? Has it got a 7 in it? Is it a square number? Can't we both a prime number and a square number? So you've got all of that mathematical reasoning going on. In a computing lesson or a computer science lesson, it's much better we want them to come up with a method that the machine could follow, this idea of the automatable solution. So what is your automatable solution to teaching a computer to play the I'm thinking of a number, guess my number game? We might do random search, or we might do a linear search, both of which really very, very slow. This one incredibly unreliable and unpredictable. This one at least slow and steady gets you there. Or we might start to come up with sort of 20 questions, yes, no, binary tree search approach to this. Is it 64 or more? Is it 32 or more? Is it 48 or more? All of which can be programmed in the primary context. So we can play this game in Scratch very easily. So here's my attempt to search binary search in Scratch. Let's go with the number 42 here. I'm thinking of a whole number between 0 and 127. Yes, it's less than 64, not less than 32. Yes, less than 48. No. Less than 44. Yes. Less than 42. No, it's not. Less than 43, yes, it is, and it's 42. This idea of a divide and conquer algorithm, of bringing the bounds of this closer and closer and closer until we get the only thing that's left. This seems to be a fundamental thing for computer science, this idea of the divide and conquer algorithm. And I think you only get to this when you're looking for automatable solutions. It's not enough just to come up with a recipe for a pizza or a recipe for a cup of tea. This gets us much closer to the ideas of computer science than an entirely unplugged. We can do this unplugged, but by coding this, by thinking, how would you get a robot to play this game? How would you get a Scratch to play this game? Gets us much closer to it. The more observant of you might have spotted that as I've been answering those questions, I've also got the binary representation of 42 there up on screen. It's an interesting pause for thought as to how that would work. Okay, let me move on. So the other example, which is really nice for that, is how do you find a book in a library? Children know how to find a book in a library. They do not go to the first book on the first shelf and keep looking through until they get to the one they want. They go to the right floor, the right shelves, the right stack, the right shelf, the right book by narrowing it down at each point. This only works if your library is in order. With a random collection of books, as we have in some secondhand bookshops here, then your approach is really just to start at the left-hand end and keep going until you get there. But once the books are sorted, once the words in the dictionary are sorted, finding the one you want is really very, very efficient. So we get ideas of algorithmic efficiency, and we get to introduce the idea of what's the best way of sorting these into order. So yes, finding automatable solutions and implementing those automatable solutions, for me, lies at the heart of computational thinking. So I'm very much in this sort of computational thinking type 1 group here. But that sort of makes me wonder, is it enough then just to focus, as Brennan and Resnick seem to, on the coding, on teaching children how to program and teaching these ideas of computational thinking through the medium of code? Simon Peyton-Jones, who I have a huge deal of admiration for as the man who chaired the work of putting together the English Programs of Study, as well as the inventor of Haskell and chair of the National Centre for Computing Education here, argues persuasively that coding is not just the medium, is not the message of the new computing curriculum, it's the medium of it too. It's the lab work of computer science. It's the thing which provides the motivation for this. And without the programming computer science, you end up with just a theoretical husk of the subject. And I worry too much about exam specifications which do that. Papert seemed to argue for a similar sort of thing, that children who'd learned how to program computers could use these models to think about thinking, to learn about learning, and enhance their powers as psychologists and epistemologists, that by learning to program, their way of thinking about problems, their way of understanding the world shifted. Nevertheless, the empirical evidence suggests there may be more to it than that. So we have this lovely code club thing happening after school in the UK. I think it's internationally now. Children do sort of an hour a week of learning to code. It's called Code Club for a very good reason. After a year's Code Club, children were doing much, much better on tests of coding. Shock horrors, no surprise there. And yet, when you gave them the Bebras type questions on computational thinking, you saw no difference in the progress they'd made over their peers who'd just been following normal computing lessons in school. So just learning to program, just learning to code, yes, helps you get better at learning to code, but it doesn't necessarily get you better at solving that sort of computational thinking problem. Interestingly, Papert sort of backtracked on his earlier argument. It didn't occur to me that anyone could take my statement to mean that learning to program would in itself have consequences for how children learn and think, which surprises me. That seems a little bit falsely naive, considering what he had written 20 years previously, but never mind. Okay, a lot of admiration for Papert. So just learning to program on its own wasn't enough. Roy P's work in 1983, you could teach logo programming, the Scratch of its day, to children in school. That wasn't a difficult thing for them to learn. But unless you also taught them how to plan, how to think ahead, then they wouldn't necessarily get better at that too. How do you go about that? Well, not flowcharts. Please, no, let's stop making them draw flowcharts. Doesn't seem to make any difference at all to how good they become at being able to solve problems computationally. I do like this idea of labeling the subgoals, of breaking the problem down and saying explicitly what the things you're trying to do at each stage of the program. Yes, I like the idea of you write the comments in your code first, and then write the code in between the comments. Anybody who's using Jupyter, write the markdown blocks first, then and only then write the Python or whatever code to go in the gaps there. So I think my final version of this diagram says, yes, we have this big domain of problem solving. Within that, we definitely do have some domain of computational thinking. And at its best, the coding belongs inside this computational thinking domain. The thing that I'm worried about most is where we put the coding outside of the computational thinking, where we just teach them how to make a maze game in Scratch without going through those preliminary stages of what are the rules of the game. How are you going to control the characters here? What algorithm are you trying to implement? So yes, coding inside computational thinking. And computational thinking as an approach to problem solving. Right, let me move on then to think a little about what this looks like in other disciplines, because I think there's a lot in common between our idea of computational thinking and what you see in other STEM disciplines. So in the mathematics curriculum in England, we have a big area of this coded in green on my slide there, which we would see as mathematical reasoning. They're dealing with increasingly complex problems, following a line of inquiry, thinking about what the relationships are, generalizing their approach to doing things, working with logic. Polya had that right in 1945 of how to solve pretty much any problem. Okay, this idea of we take this approach from mathematics and generalize it and apply it will sound all too familiar to the computational thinking type 0. This is a solution to all of the world's problems. Understand the problem, devising a plan, carrying out the plan, absolutely there. Similar thing when it comes to working scientifically, again from the English national curriculum, observing over time pattern seeking, identifying, classifying and grouping, comparing, researching using secondary sources. Really nice to see that acknowledged in our science curriculum in more detail as to what they should do. I think the most interesting work I've seen outside of just computing education is from the Royal Academy of Engineering here, with this idea of engineering habits of mind, making things that work and making things work better. I love this. Again, engineering habits of mind, some of which we have, but so much of which they are really explicit about this is how an engineer, and I would say software engineer included within this. Would computational thinking be different if it was developed by software engineers rather than computer scientists? I wonder what those differences would be. But we might come closer to this idea of thinking about the system, about finding interesting problems as well as solving those in a creative sort of way. There is rich territory in all of the STEM disciplines for finding problems there, meaningful problems where we can come up with automatable solutions to them. And let me conclude by just giving you 3 examples, all too briefly, of those now. So in our maths curriculum for, 7 and 8-year-olds in England, there's this little line as to pupils should be taught to find different combinations of coins that equal the same amount of money. There's a really, really lovely computational problem there about how many ways can you do that. There's a much easier computational problem about what's the way of doing that uses the smallest number of coins. This is a practical problem. You will be familiar with vending machines. You put money in, you get the goods. Actually, we don't put money in anymore. We use the contactless thing because, coins and things. But, back in the day, we would put coins in here and we would get the thing and change. And the good machine here would give us the change in the smallest number of coins. So with Singapore coinage, 5, 10s, 20s, 50s, dollars, what's the smallest number of coins you need to make? I don't know, $1.25. Well, $1 and a 20 and a 5. I can't think of any way of doing it in less than 3 coins. What's my algorithm for this? What's your algorithm for this? Does it typically involve taking the largest coin you can, reducing the total, taking the next largest you can, reducing the total until there's nothing left still to take? That usually seems to work. You can code that in Scratch. Given an amount of money, start taking off dollar coins until you're left with less than $1, then start on the 50 cents, then start on the 20s, and so on. We can come up with a generalized solution to that now. Let me drag this back into position so you can see my code there. So I've got initialize the coins. I'm going to use the Singapore coinage, hundreds, 50s, 20s, 10s, 5s. Let's run the code, see this working. How much money? What was it we did earlier? $1.25. So 125 cents. And it goes off and counts and says, yes, we need a 100-cent dollar and a 20 and a 5. That looks great, doesn't it? So we've got a really nice automated solution to that. You can do this a different way. You could say, what if we had new coinage, 1 cent, 2 cents, 4 cents, 8 cents, 16 cents, and so on. You will be familiar with these Bitcoin amounts. What's your smallest way of making $1.25 now? Well, that's going to be a 64 and a 32. And I'm running out of room in my head to do this. We could program the machine to do this. I'll leave this as an exercise for you. Okay. So here's my Bitcoin block. Back in the day, before 1971, England had the weirdest coinage system you have ever heard of, which had 1 penny coins, 2 penny coins, 3 penny coins, 6 pennies, 12 pennies called a shilling, 24 pennies called a florin, 30 called a half crown, 60 called a crown, 120 called a half sovereign, and 240 pennies called a sovereign. That was worth £1. So you could, again, take that code and adapt it and apply it to this. You get a really interesting result when you start applying it to 48 pence. So using that algorithm, we say, okay, take off the largest, that's 30. Then take off the next largest, that would be a 12, 42, then a 3, that gives us 42, there, then a 6, that gives us 3 coins to make 48 pence. But you can do it in fewer coins. You could do it as 2 24 penny florin coins. How come our algorithm breaks down here but succeeded in the other examples? What is the property of this list which causes that algorithm to break? Really interesting problem to investigate. There are solutions to it. One of them involves recursion and is incredibly slow. Another might include this idea of keeping track of the numbers you've got to so far. I have Scratch code for that in the slide deck. Taking from the domain of science, this idea of how do you model the spread of a pandemic? We have there this idea of we observe things and we see what happens. You can't do that if you want to try interventions within the spread of a pandemic, but you could model that on a computer. So identify the set of rules in order for something to happen, and then program the machine to apply those rules. So we have a very simple model. It's the susceptible, infected, recovered model of the spread of a disease here, modeled in P5.js, this lovely version of processing which runs inside the browser here. So all I'm saying is if when they touch one another, there's a probability that they pass on the infection. So we can set that running and see what happens there. So I have at the moment 50% of my population staying at home and really sort of spiking up with the number of people infected at any one time. That's 64 of my 100 balls moving around the screen here. If I, in fact, make 80% of people stay at home, let's run that and see what happens to the curve now. Much, much slower. So our health service can cope with that. And this is a teachable thing. I wouldn't do this at primary school, but this is a really nice introduction to object-oriented programming. You've got to include and understand the rules, but you've also then got to be able to apply those. From technology, from engineering, from design and technology, I think my favorite example is programming a robot to solve the Rubik's Cube. Familiar with the Rubik's Cube? There are standard algorithms. I've highlighted the word algorithm there in the online book or set of instructions for how to solve the Rubik's Cube, which says, before starting the algorithm, there's an if-then statement to apply that. Conditional logic is included there. You can get apps for this. There's a website which you can show it the state of your cube, and then it will come up with the optimal, the most efficient sequence of steps to follow, not the general algorithm, but a particular one for this particular case. And then, of course, because this is engineering, because this is design and technology, we want to build the robot to do this. And there are build instructions out there for the Cuba robot using Lego Mindcuber, robot using Lego Mindstorms to create a machine that will solve the Rubik's Cube. Okay, physically it can do it, but then you've got to have the code for that. And again, folks have written programs for how to go implement that general algorithm for solving a Rubik's Cube as code, or implement an optimized version of that. Right, okay, so we are pretty much there. I want to leave some time for Q&A at the end here, but let me just conclude by summarizing where my thinking is around computational thinking. I'm very much of type 1 computational thinking here. It is about finding those automatable solutions, ones which could be implemented by a machine. I think, as do Tedder and Denning, that this is a thing worth doing, being able to program a computer to solve problems that you could not solve yourself is a skill worth teaching to everybody, not just the programmers, computer scientists, software engineers of the future. But this is a thing which is so important. Just as we teach poetry and music to everybody in school, that this is a thing worth teaching to everybody. I think you get so far with teaching the parts of computational thinking, but it's only when you apply it to finding those automated solutions that it really comes into its own. I do think you can lay the foundations of it really early on by getting them to plan ahead, by thinking about sequences of instructions. And that can carry on a long way. How would you play this game? What's your best move to make in these situations? I do have a lot of respect for the unplugged approaches, and they help in finding out what the best solution is, whether it's with a Rubik's Cube or modeling the spread of a pandemic or finding a word in a dictionary. The unplugged approaches have their place. The coding, the actual implementation of that is really important. Just stopping at, okay, you found a solution, is unmotivating for your pupils and doesn't empower them to actually use the computer there to solve the problem. Is not the only thing that matters. You've got to teach the planning as well. I think there is a big overlap between computational thinking and the sorts of thinking that is encouraged in other STEM disciplines. And look to your colleagues teaching STEM disciplines for really interesting, motivating contexts for finding those automatable solutions. The whole thing on one slide. Should have started with this one, really, shouldn't I? Okay, time for discussion, really, now. Let's change that to discussion. No, it can't be, because I'm the only one who gets to answer here. If you want to have a look at the slides again, most of them have got links to the supporting materials. Then this URL, let me see if I've got, I'm not sure if I've got access to the chat. I think I might be able to do that there, but I don't know whether that's worked for other people. So you've got access to the slides and you can follow up most of the references there. I'll stop talking and hand back to Bimlesh to attempt to chair some Q&A for this. Thank you so much.
Thank you so much, Miles. It was so interesting to listen to various perspectives on CT and unpacking the definitions and bringing it back to us, all kinds of definitions of computational thinking we have seen in research and in literature, and making us think about the game name once again. I mean, after many years, I was looking at it, and that was very interesting. And then you took us through the history of computing and shared your own perspective on how do you see problem solving, computational thinking, and coding, and how your Venn diagram changed over the years. And then linking it perfectly well with the STEM areas. Yeah, lots of examples there for all of us to think through. So thank you once again, and let me take some of the questions.
Pleasure.
I think the first question I have in the chat is there any relationship between computational thinking and critical thinking?
I think there is, and I think History's definition attempts to say computational thinking is critical thinking with computing. I'm not entirely sure what we mean by critical thinking. I would very much include logical reasoning as part of both. And I want pupils emerging from primary and indeed secondary school being able to think critically, being able to argue their case persuasively. Back in ancient Greece, the three parts of the curriculum starts with logic and then grammar and then rhetoric. That logic has been foundational to education from Plato's day onwards. And I think computational thinking relies on logic. And whatever your working definition of critical thinking is, I think critical thinking ought to rely on that as well. In computing, we see it in terms of what will this program do? Why is this not doing what I wanted it to? Debugging provides such an opportunity for that logical reasoning, that critical thinking. Again, I'm moving into the domain of code, of automated solutions here, rather than just sitting at that abstract layer of algorithms. And why is this recipe for a cake better than that recipe for a cake? No, let's test it and see. But when it comes to the coding, I think you get the best results by getting children to read the code and find the bugs by hand, rather than asking the interpreter to highlight where the mistakes are in the code or testing it. I think going through the reasoning about it logically is so important. I've been working with our undergrads across programs at the university recently on an introductory programming course for them. And some of the best fun we've had is that here's a program that doesn't work. Can you fix it? And again, I just repeat myself, the ones who think about it logically do better. The same should apply to critical thinking more generally. Can you read this argument in history? Can you read this response to a question about a controversial topic and see where the weak points in the argument are? Can you debate this? Paying respect to the other person's position and argument, and still see where the weaknesses are. Okay.
Yeah, I agree. I hope the audience who had put the question agrees with the answer. And I also think that thinking skills, all of them have some overlaps with each other. They're not really mutually exclusive in that sense. We may have time for one or two more.
My point really, that without the computational thinking becomes just generic thinking skills. And I think we have more to offer. I think we have more to teach than that taking this approach to solving a problem, but then getting the machine to do it for you lies at the heart of this for me. Sorry, Bimlesh, I interrupted.
Yeah, no worries. I think it's we are lacking that interaction with the audience, which I think you and me both feel at the moment. So there is one more question in the chat, and I'll read it to you. So I think you talked about the concept of game name, and this question came after that. So in practice, have you found most K-12 students understand the concept of a game tree, for example, for NIM? And how many of them are able to program an implementation, a complete implementation, to play the game optimally?
Okay, not so much in primary. I think, you playing the game is achievable from even a very young age. 5, 6, 7-year-olds are able to play NIM against one another and against the computer. I think certainly by the age of 8 or 9, they're spotting that there is a strategy to playing this game well. They're seeing that there are certain positions that the game board can be left in that always will result in a win. Reasoning about that logically or critically, I know this is going to be a win because is much, much higher order. And I think that's lower secondary if you're lucky. Implementing it as code is later. It really is, because the patterns here, if you're going to go with this is a winning move because of this bitwise XOR coming to 0, this is quite a subtle idea which requires quite a deep understanding, and understanding why that is. That's, I think, first year undergraduate in quite an academic university, I suspect. And I wouldn't necessarily rush into coding NIM, but getting to the point where they recognize that there are winning moves and a computer can be programmed to play this, I think is worth doing. There are easier games to code. So my Guess My Number game, much, much easier to get pupils programming a version of that. And that's definitely accessible. I've taught it myself with 10, 11-year-old students. You can get, but by the time they're leaving primary school, to them being able to implement a version of binary search for at least positive integers. Okay. I think that's pretty much it. Listen, if you're still watching, it has been such a pleasure to be able to share some of these thoughts with you. Feel free, please, to get in touch via email or via the Twitter thing after the conference. As I said, let me pop the slides. Oh, okay. I've got another question appears here. Let me read this. Member's definition of CTE is not the same as Coding Club. Measurement of CTE should be suited to the assumptions about CTE's definition. Absolutely. You've got to have an idea of what it is you're trying to measure before you can measure it. And the Code Club really didn't pay very much attention to this idea of computational thinking. The name is, the clue is in the title of the club there. This was a focus on coding. And their members did really well when it came to a test of coding. They never claimed to be developing computational thinking, but it just provides further evidence that programming on its own isn't enough to develop computational thinking. If you want to teach something, then you basically have to teach it. I will pop my contact details back up on screen, because listen, you really would be very, very welcome to get in touch via email or the Twittery thing. As I say, the slides are all online if you want to follow up on any of this with the original sources. I'll stop sharing. Right.